Hi everybody, I'm Kevin Sung. I'm a software developer at IBM, and today I'll be talking about mapping problems to qubits. So in the context of the Qiskit pattern workflow, well, there's four steps in the pattern. First, we map the problem to quantum circuits and operators. Next, we would optimize the circuits for the target hardware. Then we execute our circuits on the hardware. And finally, we post-process the results. So in this lecture, I will be solely talking about the first step, the mapping step. And in this lecture, I will cover two applications: combinatorial optimization and quantum chemistry. Okay, so let's talk about combinatorial optimization. In combinatorial optimization, the goal is to find an input that maximizes or minimizes the value of a cost function. So here I've written the cost function as c, and the input is x, and I want to find an input that maximizes the value of the function. So some examples. One would be the knapsack problem. So this is a problem from computer science. So here you have a knapsack that can fit a limited set of items. The input x would be the selection of items to include in the knapsack, and the items have different values. And the cost function would be the total value of the items that you put in the knapsack. And a somewhat more practical sounding example would be the vehicle routing problem. So here you have a fleet of vehicles and you want to choose routes for them in a way to minimize the total distance. Here x would be the routes for the vehicles, and the cost function c of x would be the total distance traveled by all the vehicles. So this would actually be a minimization problem. Many combinatorial optimizations are too difficult to solve exactly in practice. So often we settle for approximate solutions. And the quality of an approximate solution, x, is quantified by the approximation ratio, which is just the cost function value of the solution divided by the optimal value. So here, opt is defined as the maximum possible value of the cost function. So if the problem is too difficult to solve exactly, then we wouldn't actually know the true value of opt. However, sometimes we are able to get a lower bound on it. In this lecture, I'll be giving an example of a specific problem that we will map to qubits. And the specific problem I'll be talking about is the max cut problem. So the max cut problem is a graph problem. So we're given a graph, and the goal is to partition its vertices into two sets such that the number of edges between the two sets is maximized. So on the slide here, I have a picture of a graph, and I've also depicted a partition of the two vertices. So the color of the vertices indicates which set of the partition it's in. And given this partition, some of the edges will be cut, and that's depicted by the color of the edges. So here the purple edges are cut, and also by the black dotted line, which shows the edges being cut. Now, the decision version of the max cut problem is a canonical example of an NP-complete problem. So this class of problems it's very difficult, and in general, we don't expect to be able to solve this problem exactly in practice. Now I'm going to give some definitions that will help us obtain a computer representation of this problem. So first of all, a partition of vertices into two sets is called a cut. And the size of a cut is the number of edges between the two sets of the partition. So in this example here, the size of the cut is 5 because 5 of the edges are cut. And now I can state the goal of the problem is to find a cut with the largest possible size. Now, as I get closer to the computer representation, a cut can be represented as a bit string, a sequence of zeros and ones. So here, there's one bit for each vertex, and the value of the bit indicates which set the vertex belongs to. So 0 means it belongs to one set, and 1 means it belongs to another set. And the goal here is to find a bit string that maximizes the cost function. So here I've written the cost function in a form that takes the bit string as input, and it's a sum of terms where the sum runs over the edges, and each edge will contribute a term, and the edge will contribute a 1 if that edge is cut by the partition, meaning that the vertices of the edge are different from each other. So given a bit string that represents a cut, this expression here will give you the size of the cut. So now that I have the cost function, I can state the goal of the max cut problem as to find a bit string that maximizes this function here. So we're gonna do a little trick here where we do a change of variables. So the bits that I've represented with B are zeros and ones, and we're just gonna do a change of variables so that they become plus and minus 1 instead of 0 and 1. And using these new variables, I can actually express my cost function using arithmetic operations. So here the z variables are being multiplied, and they're plus and minus 1, which means that if they differ from each other, this is going to be a minus 1, and this expression is going to evaluate to 1, which is what we wanted. And if they're the same, this expression is going to evaluate to 0, which is also what we wanted. And I'm just going to mention briefly that this is an example of what's known as the Fourier expansion of a Boolean function, which is where you express a Boolean function as a polynomial of the bits. So now that I have changed my variables, I can write my cost function like this here. And the final trick is to promote these plus and minus 1 variables to quantum variables. And the way that it works is that I will replace each of these plus or minus 1 variables, which I notated with z. I'm going to replace each of them with the poly z operator, which is similar to a plus or minus 1 variable because it's just diagonal matrix with plus and minus 1 on the diagonals, right? And if I do that in this expression, well, the poly z matrix, the poly z is a matrix, which means that this becomes an operator. Basically, it's a big matrix, and it's a quantum operator. And here I'm abusing notation a bit and writing C for both for the objective function and the quantum operator here. So it's not that egregious of an abuse of notation, because if I take this quantum operator and I act it on a computational basis state, all that happens is that that basis state gets multiplied by a factor that's equal to the cost function. So this quantum operator really is representing this cost function. And because of this expression, I can also write, if I have a computational basis vector, I can also write this expectation value. And this expectation value will just be the value of the cost function on that bit string. And this operator is called the max cut Hamiltonian. So in the context of quantum mechanics, a Hamiltonian is just a linear operator that's Hermitian. And in terms of matrices, it just means that it's a matrix whose conjugate transpose is equal to itself. Okay, so I now have the max cut Hamiltonian, which is a quantum representation of our cost function. And to get a bit more concrete of what it looks like, it's a 2 to the n by 2 to the n diagonal matrix, and its diagonal entries are the values of the cost function. So here I've written what the matrix actually looks like, and I've reverted to 0 and 1 for bits to match the quantum computing convention. And now I can restate the goal of the max cut problem as I want to find a computational basis vector with the highest eigenvalue of this max cut Hamiltonian. So the max cut problem originally arose in the context of classical algorithms, and the classical strategy for solving this problem would be to sample a bit string from a probability distribution generated by an efficient classical algorithm. And the best known algorithm for this is what's known as the Gomans-Williamson algorithm, and that achieves an approximation ratio of about 0.878. The quantum strategy for this problem would be to prepare a quantum state on a quantum computer using an efficient quantum algorithm, and then measure the state in the computational basis. This will give you a bit string, which will be your solution to the problem. Now, because quantum computing is a generalization of classical computing, the quantum strategy can only be stronger than the classical strategy. It's at least as strong, that is. And there's a crucial conjecture here, which is kind of underlying the field of quantum computing, which we can call the quantum advantage conjecture, is that the quantum strategy can sample from more and better probability distributions than the classical strategy, which is to say that the quantum strategy can actually give you better solutions than the classical strategy, or solutions faster. And I'm just going to briefly show here an example of how you would map the problem onto circuits. So far I've shown how you would map it onto an operator, right? And there's a common algorithm for addressing the max cut problem called the QAOA, which stands for the Quantum Approximate Optimization Algorithm. And here you have the max cut Hamiltonian, but you also have another Hamiltonian, which is sometimes called a driver Hamiltonian, and it's the sum of single qubit X operators. And you have an initial state, which here is the sum, the uniform superposition over all computational basis states. And then you have the QAOA ansatz, which is a quantum circuit or rather a state where the circuit is constructed by applying alternating applications of time evolution by either the max cut Hamiltonian or the driver Hamiltonian. And the evolution time here are free parameters. So in practice, you would optimize these parameters here in order to maximize the cost function. And so the QAOA circuit actually has an interesting theoretical motivation behind it. I'm not going to get into the details, but it's a common example of a circuit that you would use this to address the max cut problem. And in the next lecture, Daniel Egger will be diving into more detail about optimization. So look out for that lecture. Okay, so that's all I'll say about combinatorial optimization. And the rest of this lecture will be about quantum chemistry and how we map problems in quantum chemistry onto quantum computers. Okay, so a basic question in quantum chemistry is you're given a configuration of atoms and you want to know its properties. So here I'm depicting a very simple example. So this is a water molecule, H2O, right? You have two hydrogen atoms bonded to an oxygen atom. In a water molecule, the bond between the hydrogen and the oxygen has a certain length, and the angle between the hydrogens has a certain angle, and we can actually measure these quantities in a laboratory. However, what's also cool is that we can actually input this information, or the configuration of the atoms, onto a computer, and because we know the laws of quantum mechanics, we can actually compute the bond length and the angle. We can compute these quantities on a computer. So this is water, which is a fairly small molecule. So we can handle these on classical computers. However, the best known algorithms for calculating properties of molecules, they scale exponentially with the size of the molecule or some other measure of the size of the problem, which means that if we want to have accurate solutions on classical computers, we can only handle very small systems. And once the system gets to a certain size, our algorithms can no longer compute these properties. And that's why predicting the properties of molecules and materials is one of the most anticipated applications of quantum computers. So in the setup of chemistry, we have a number of nuclei and electrons, and they're arranged in some configuration, and we can define these variables that represent the distances between the nuclei and the electrons, the various particles. And the state of the system is represented by a wave function, which is a function of the coordinates of the particles. And the energy of the system is represented by a Hamiltonian. And here I've written the Hamiltonian, the molecular Hamiltonian. It's an operator which maps functions to functions. It's a sum of various terms. Some terms represent the kinetic energy, which is a derivative operator, and then we also have terms representing the interactions between the various particles. Now, the molecular Hamiltonian that I showed is a pretty complicated expression. Often in chemistry, we make what's called the Born-Oppenheimer approximation to simplify the problem and make it a bit more amenable to calculation. And the idea of the Born-Oppenheimer approximation is that nuclei are much more massive and therefore they move much slower than electrons. So let's just treat them as fixed points. So if we do this, then the kinetic energy of the nuclei is 0, and the interaction between the nuclei is just a constant. So we can drop these terms from the Hamiltonian, and the result is what we call the electronic Hamiltonian, which only contains the terms that involve the electrons. So we still have the kinetic energy of the electrons, and then we also have the interaction between the electrons at the nuclei and the electron interactions. And here, the R here reminds us that this Hamiltonian actually is parameterized by the by the positions of the nuclei. And often in chemistry, the goal is to solve the Schrödinger equation for this Hamiltonian, which means finding its eigenvalues and eigenvectors. And often we're interested in the low-lying eigenvalues and eigenvectors. So, okay, so we have now the electronic Hamiltonian, which is this operator that acts on a space of functions. It involves derivatives. So it's a continuous object. To represent the Hamiltonian on a computer, we need to discretize it somehow. And there's different ways that you can discretize this Hamiltonian to represent it on a computer. In this lecture, we're going to focus on one of the methods, which is called second quantization. And here I've written the Hamiltonian, the form of the Hamiltonian in second quantization. So here the HPQ and the HPQRS are just numbers. The A and the A daggers are quantum operators. You can think of them as big matrices. So in the discretization, we've gone from this continuous object that involves derivatives, and we've transformed it into a big matrix. And now I need to tell you about these A and A dagger operators. So the idea of second quantization is that electrons will be described by a system of fermionic modes. They're called fermionic modes because we're dealing with fermions, which is the category of particles that electrons belong to. And a system of n fermionic modes or orbitals. So modes and orbitals are the same thing. The terms are interchangeable. A system of n fermionic modes is described using a set of n fermionic annihilation operators. These are the A operators, and these operators satisfy the fermionic anti-commutation relations. So these operators satisfy some equations. And the adjoint, the A dagger terms, which is the adjoint of an annihilation operator, is a creation operator. Now let's look at these relations and try to understand them. So the first one is saying that it says AP times AQ plus AQ times AP equals 0. Because these two terms add to 0, that means one of them is the negative of the other. And these terms basically look the same, right? It's just that P and Q are swapped. So this is saying that if I have a product of two annihilation operators, if I change the order, then I pick up a minus sign. And another way of saying that is that AP and AQ anti-commute. For the second relation, this is telling us the relation between an annihilation operator and a creation operator. So if they act on different modes, then the Kronecker delta is going to be 0, which means that they still anti-commute. However, on the same mode, if P and Q are the same, then this expression adds up to the identity operator. So from these fermionic anti-commutation relations, we have a set of operators and they satisfy these relations. It turns out that you can actually tell a lot about the structure of the vector space in terms of these operators. It turns out that the operators AP dagger AP, these operators commute and they have eigenvalues 0 and 1. And these are called the occupation number operators because they tell you the occupation of a mode. Remember, the way that we're thinking about this is that the fermionic modes, each mode can be occupied or not occupied by an electron. And these occupation number operators tell you the occupation of the mode. There is a normalized vector called the vacuum state, which is a mutual zero eigenvector of all the occupation number operators. So this is the state that has no electrons in it. If I have a state which is a zero eigenvector of the occupation number operator, then if I act on this state with a creation operator, AP dagger, then it's going to be a 1 eigenvector of that occupation number operator. So this is why we say that AP dagger creates a fermion in mode P. And similarly, if I have a 1 eigenvector of the occupation number operator, then the annihilation operator, AP, will turn it into a 0 eigenvector. So that's why we say that AP destroys a fermion in mode P. We also note that the creation and annihilation operators square to 0. And this is one manifestation of the Pauli exclusion principle. And the way that you can interpret this is that if I try to create an electron in the same mode twice, well, you can't, because the result is just 0. And finally, we can actually construct an orthonormal basis of 2 to the n vectors labeled by bit strings, z. And the bit strings are going to be of length n, and the value of the bits are going to tell you whether or not to apply the corresponding creation operator to the vacuum state. So here, we're starting from the vacuum state, and we're applying some subset, some combination of creation operators to it. So we're creating electrons in various modes. And these basis vectors are called Slater determinants. It sounds like the terminology might sound a bit obscure, but later on we will see where the terminology comes from. So we can also figure out how an annihilation operator acts on the basis vectors that we just constructed. So if I take an annihilation operator for mode P and I act it on a basis vector represented by a bit string, if the corresponding bit is 0, which means that that mode is not occupied, then if I apply the annihilation operator, I'll get 0. If the mode is occupied, which means there's a 1 there, then when I apply the annihilation operator, it'll flip that 1 to a 0. But we also pick up a coefficient here, which is it's a phase factor. It's going to be plus or minus 1, and it's going to depend on the parity of the preceding bits. Right? So here I'm destroying an electron in mode P, but we're picking up a phase that depends on not only on that mode, but also on all the other modes. And this behavior differs from qubits, right? Because if in qubit land, if I apply an operator to a subset of qubits, that operator is going to be tensor product with the identity on the rest of the qubits, which means that the state of the rest of the qubits is not going to influence the action of that operator. It's different here because I'm annihilating just on mode P, but I pick up a phase factor that depends on the occupations of the modes that precede P. And the consequence of this is that the notion of locality differs between qubits and fermionic modes. And this is going to be an important consideration when we map fermions onto qubits. So what we have so far is that a system of fermionic modes is represented using fermionic creation and annihilation operators. On the other hand, when we are dealing with qubits, usually we represent our operators using tensor products of the Pauli operators I, X, Y, and Z. So this raises a question: how can we represent the fermionic operators using Pauli operators? So just based on the action of the annihilation operator from before, we can make a first attempt, because there's an operator which is sometimes called the qubit destruction operator, right? We can try mapping the annihilation operator onto this operator here, and here, this expression here is an operator which takes the one state to 0 and it annihilates the 0 state. If I apply this to the 0 state, I just get 0. And here I've written the 2 by 2 matrix that this operator represents. And I can also write it in terms of the Pauli X and Y matrices. And if I take this operator and I act it on a bit string, well, for if the pth bit is 0, then AP applied to it will indeed give you 0. And if it's 1, then it will indeed flip it to a 0. However, the phase factor is missing. To fix this, what we can do is we can add what's often called a Z string. So this is going to be a string of Pauli Z operators. So here, in addition to having the destruction operator on qubit P, we also have Z operators acting on qubits 1 through P. So here I've expanded out the expression. So I have my destruction operator here. For the higher qubits, it is indeed just the identity operator. But then for the lower qubits, we have Z's on all of them. And this string of Z's will indeed compute the phase that we wanted. So if you define your operators like this, then you'll have a set of operators expressed in terms of the Pauli matrices, which do satisfy the fermionic anti-commutation relations. So these operators are a valid representation for your system fermions. And this representation is called the Jordan-Wigner transformation. So something important to notice about the Jordan-Wigner transformation is that, as I said before, operators that are local in terms of fermions are not local in terms of qubits, right? Because this operator is local in terms of the fermions because it's simply destroying a fermion in mode P. However, the qubit operator, it acts not only on the pth qubit, but also on qubits 1, 2, up to P minus 1 with the Pauli Z, right? And we can think about this as introducing an overhead in the simulation. I have fermions, I want to simulate them with qubits. There's an overhead that results from the introduction of these Z strings, and the overhead is O of n. It's linear in the number of modes or the number of qubits. If I have my annihilation operator that acts in the last mode, then we would have a Z string on the rest of the qubits, and that operator would actually act on all of the qubits at the same time. However, the Jordan-Wigner transformation is just one of many possible fermion to qubit mappings. It's one of the most popular because it's very simple. There are other ones, and it turns out that using something called the Bragi-Kitaev transformation, the overhead can be reduced to O of log n. So that's pretty cool. I'm not going to describe it here, but if you're interested, you can read about the Bragi-Kitaev transformations to see how that works. Now, just to give you a few examples of how common operators map under the Jordan-Wigner transformation. So the occupation number operator maps to just basically a single qubit Z operator. So this operator is local. It only acts on qubit P, and it's just a Z operator. It's shifted and scaled, but it's just a Z operator. The tunneling interaction, which is this thing I've written here, so it acts on two modes, right? And it kind of represents electrons hopping between these modes, right? Creating in one, destroying in the other. And we're adding the complex conjugate so that this is a Hermitian operator. And this gets mapped onto an XX plus YY interaction in qubit land. However, we also have this Z string going between qubits P and Q. So it acts on qubit P, qubit Q, but then also the ones in between. However, from this expression, we can see that if the modes are adjacent, so if Q is P plus 1, then this qubit operator is actually local, right? We don't have the Z string anymore because these modes are adjacent. It's just XX plus YY on adjacent qubits. So this is a 2-qubit operator. And yeah, so the upshot here is that if, at least for the Jordan-Wigner transformation, often if these operators are next to each other, the Z strings will cancel each other out. And that's something that's very useful to take advantage of. Okay, so now I'll give an example of mapping a circuit, a fermionic circuit, to a qubit circuit. And the example I'll take is the orbital rotation. The orbital rotation is a fundamental operation in fermionic simulations. And here the orbital rotation is represented by this calligraphic U. And the way that it maps an annihilation operator is it takes the annihilation operator and it maps it onto a linear combination of annihilation operators. And I'll just write that linear combination as BP. So it maps AP to BP. And here the coefficients of the linear combination, they form a unitary matrix. And here, I'd like you to notice that the U in normal font here is an n by n matrix. So it's a small matrix. Calligraphic U here is 2 to the n by 2 to the n. It's a big matrix. So we have a small matrix, and that describes a big matrix. It turns out that these BP operators, they also satisfy the fermionic anti-commutation relations. So I've written these relations here in terms of the BP operators. And because of that, the BP are also fermionic annihilation operators. They destroy fermions in a different set of modes related to the original modes by a basis change. So really the orbital rotation, all it does is it's a change of basis from one set of modes to another set of modes. And a qubit analogy for this would be changing from the Z basis to the X basis. With qubits, if I want to do a single qubit, we'll change from the single qubit Z basis to the X basis. On all the qubits, that would just be a single layer of basis change gates. However, with the orbital rotation, it's going to be a bit more complicated than that. Now, As an example of an application of the orbital rotation, here I have the expression again for the molecular Hamiltonian, and you can actually think of the Hamiltonian as being composed of two terms. This part is often called the one-body term, the one-body part, and you have the two-body part here. And the one-body part is a quadratic Hamiltonian, which means that the terms have products of at most two fermionic creation and annihilation operators. And a useful fact is that any quadratic Hamiltonian can always be rewritten in a diagonal form. So here it's rewritten as a sum of, or a linear combination of occupation number operators on a different set of modes. So the original modes are A, the new modes are B, and in this new basis of B modes, the Hamiltonian is just a sum of occupation number operators, which is diagonal, and therefore this can be simulated easily. So the conclusion is that just by doing an orbital rotation, we can make this a one-body part of the Hamiltonian diagonal, so we can simulate it easily. And I'll just mention really quickly that it turns out the two-body part can also be simulated with orbital rotations using what's called the double factorized, or also known as the low rank representation of the two-body part. So how do we implement an orbital rotation on a quantum computer? Well, an orbital rotation is represented by an n by n unitary matrix U. And the goal is to apply this big U that's being represented on a quantum computer. And there's a useful fact which we'll use, which is that the map from little u to big U, right? This map actually satisfies what's known as a group homomorphism property. All that means is that if I multiply small matrices together, the big matrices also get multiplied. And we'll take advantage of this because we're going to take our unitary matrix U and we're going to do a decomposition of the unitary. It's kind of like with a unitary you can do a QR decomposition. It's similar to that. Here we're decomposing it into a sequence of operations. D is a diagonal matrix, and G, these are going to be Givens rotations, which I'll explain in a bit. And this decomposition of little u is going to yield a corresponding composition of big U in terms of basic gates. Now, a Givens rotation is it's a matrix that is a rotation matrix in a two-dimensional subspace. So here the Givens rotation is going to be parameterized by P and Q, which are the modes that it's going to be rotating together, and then there's going to be angles, theta and phi. So phi is needed in case we need to introduce complex phases in the rotation. And this Givens rotation here will represent a certain operation on the Hilbert space of quantum states. And the way that this operation acts on the fermionic modes P and Q is it acts as a rotation. So it's going to change the annihilation operators from modes P and Q into linear combinations of each other. And that can be written in this simpler form, or this matrix form, where the annihilation operators are simply getting mapped onto a rotation matrix applied to those operators. And It turns out that this operation here, rotating two modes, can be achieved by this unitary that I've written here. So these are the I, phi, AP dagger, AP terms. These are just complex phases. And the real, or the more interesting part of the operation is this rotation here, which acts on two modes. And this is the operation that affects this Givens rotation. So yeah, so the strategy for implementing an orbital rotation is we're going to decompose U into a diagonal matrix and a sequence of Givens rotations. And we're going to apply the sequence of Givens rotation gates defined by those Givens rotations. And then the diagonal factor can be implemented using these phase gates. What I mean when I say that these are phase gates, so as we saw before, the occupation number operator, so this is just the occupation number on mode P, and that maps onto, up to a shifting and scaling, it just maps onto a poly Z operator. So this is just a single qubit Z rotation in the qubits. So we have the same gate here. This is just a single qubit Z rotation. It's a very easy operation to achieve. Now, this rotation gate here, it acts on two modes, and in general, there would be a difficulty because these, even though it acts on two fermionic modes, we saw before that in terms of qubits, it might not be local, and it can introduce the Z strings, right, between P and Q. However, if P and Q are adjacent, then this is a local operator, and it is, in fact, just a 2-qubit gate. Again, if P and Q are adjacent, this gets mapped onto a 2-qubit gate. So it would be nice if we could perform this Givens rotation decomposition in a way where the Givens rotations act on adjacent indices, because that would give us a sequence of 2-qubit gates, which furthermore just act on adjacent qubits. It turns out that this is possible, and here I'm just showing a picture of what the orbital rotation actually looks like when it's compiled down to qubits. So first of all, you'll notice that there's two circuits that are independent from each other. That has to do with the spin variable, which allows you to parallelize the orbital rotation across the different spins. So I'll explain spin in a bit, so we'll ignore that for now. If we look at just like one of these circuits, we can see these XX plus YY gates, which represent the Givens rotations. And as you see, they are acting on adjacent qubits. And another nice property is that they're very dense, so we're fitting as many gates as possible into as few layers as we can. And so this is a visual representation of the Givens rotation decomposition of the unitary matrix. And the phase gates here are implementing the diagonal. Okay, so now that I've talked about mapping fermions onto qubits, in terms of the operators, and give an example of the circuit, I'm going to conclude by briefly explaining a bit how the discretization works. So as I said before, we started with this electronic Hamiltonian, which is this continuous object that involves derivatives, and we obtained the second quantized Hamiltonian, which is just written in terms of matrices that can be represented on a computer. So the idea of the discretization is we're going to choose a finite set of functions to represent the space of functions, and we're going to project the Hamiltonian onto the space spanned by these functions. So we're going to start by choosing a finite set of what we'll call spatial orbitals to represent a function of a single electron's position. And here the spatial orbitals are just these functions that are represented by phi. And what this is showing is that we are going to represent the spatial functions, or the functions of a spatial coordinate r. They're going to be represented as a linear combination of these spatial orbitals. And see, in general, if you have an arbitrary function, you're not going to be able to represent it just using a finite linear combination like this. So that's something that we have to accept, because on a computer we can only represent a finite number of things. If the more functions that we include in the more spatial orbitals that we use for our expansion, the more accurate this can be. So describing an electron requires not only describing its position, but there's another property of electrons called spin, which I mentioned before. And the spin is going to be described by two orthonormal functions, alpha and beta, representing spin up and spin down. And we use these spin functions together with the spatial functions to construct spin orbitals. And a spin orbital is going to describe both position and spin. And a spin orbital is going to be a product of a spatial function with either the alpha function or the beta spin function. And the result is that the coordinates for an electron include position and spin. So once we have these basis functions, these spin orbitals, how can we build a many electron wave function from them? Well, a fundamental postulate of quantum mechanics regarding fermions states that a many electron wave function must be antisymmetric with respect to exchanging the coordinate of any two electrons. So the wave function is a function of the electronic coordinates, and what this postulate is saying is that if I exchange two coordinates, so here I'm taking xi and xj, and then I'm swapping them to get xj and xi, the wave function picks up a minus sign. So if I have my spin orbitals and I want to construct, well, the spin orbitals are functions for a single electron, right? And I want to construct a 2-electron wave function. One thing that I can try is to just multiply the spin orbitals, right? So my function of 2 electrons is just going to be the product of spin orbitals. The issue with this is it's not anti-symmetric, right? However, we can fix it by forming this linear combination here. So with this expression, if I swap x1 and x2, then I end up with the negative of this expression. So this expression does satisfy the anti-symmetry property. So now that we have a way to build up anti-symmetric wave functions using from our spin orbitals, at least for 2 electrons, we can try to generalize this. So we can take this expression and we can actually write it as a determinant of a matrix, a 2 by 2 matrix. And this allows us to generalize because for n electrons, we can form this determinant of an n by n matrix. And this is also going to satisfy the anti-symmetry property. So this gives us a way to build up an anti-symmetric wave function from spin orbitals. And this wave function here is called a Slater determinant. So in this expression for the determinant, we we only need to specify the spin orbitals that appear in the determinant in order to be able to reconstruct this. In other words, we can actually create a more simplified notation for this later determinant where we just list out which orbitals appear, because just from this information we can form the determinant. So the way that we would describe this state in words is in this Slater determinant, the orbitals chi A, chi B, up to chi C are occupied. And the order of the orbitals actually matters because of the antisymmetry principle. If I swap two of the orbitals, then I pick up a minus sign. So earlier in this lecture, I had also referred to some states as Slater determinants. Those were the bit string states that we constructed by applying creation operators to the vacuum state. So those are indeed the same states, and the connection is given by this expression here. So if I start with a vacuum state and I apply a creation operator to it, then I get a Slater determinant. So here I'm creating an electron in mode P, and the result is the Slater determinant with mode P occupied. To give an example of this, with 8 orbitals, if I have orbitals 1, 2, and 4 occupied in the Slater determinant, that would be the same state as taking the vacuum state and applying creation operators 1, 2, and 4. And in terms of bit strings, well, the bit string is going to have length 8, which is the total number of orbitals, and bits 1, 2, and 4 are going to be set to 1, and the rest of them are going to be 0. So this is the connection between Slater determinants and creation and annihilation operators and bit strings. Okay, so how do we actually get these spin orbitals in practice? So one common method, which is fundamental to quantum chemistry in practice, is called the Hartree-Fock method. And in the Hartree-Fock method, it can be seen as a way of approximating the ground state of the electronic Hamiltonian as a single Slater determinant. So again, the goal is to compute the lowest eigenvector, right? And in general, the lowest eigenvector of the Hamiltonian is not a Slater determinant, but let's just take the best approximation, which is a Slater determinant. And in this expression, psi is a Slater determinant. And to find the best Slater determinant, we would optimize over the choice of spin orbitals. To actually implement the Hartree-Fock method on a classical computer, we would choose a finite set of spatial basis functions and use them to represent the spatial part of the spin orbitals. So here, I have written this expression here, which is showing that, again, for a function, we're going to represent it as a linear combination of the spatial basis functions. And the energy that we get as a result is going to depend on the choice of basis functions. And the basis functions are going to form what we call the basis set. And often these functions are constructed from Gaussians. And the more functions that we include in the basis set, the more accurate the result's going to be. Okay, so once we have our spin orbitals, we can finally say how to actually get the discretized Hamiltonian. So again, we started with the original Hamiltonian written in terms of derivatives. And to get the matrix form of this Hamiltonian, it turns out that the coefficients are going to be given by these integrals of the spin orbitals. And that's all I'll say about this. And if you want to learn more about the details, you can consult a book on quantum chemistry. Okay, so to review now what we covered in this lecture, we talked about problem mapping. And first we talked about problem mapping for combinatorial optimization. So the steps for the mapping here would be first you write the objective function in terms of binary plus and minus 1 variables. Then you convert the objective function to a diagonal Hamiltonian by substituting the binary variables with the Pauli Z operator. And then you would design a quantum circuit and measure its output state in the computational basis to obtain a solution to the problem. For quantum chemistry, the steps would be, well, first you would discretize the electronic Hamiltonian using second quantization. So this would involve getting a set of spin orbitals, for example, using the Hartree-Fock method, and then writing down the Hamiltonian using creation and annihilation operators. Then you would map your fermionic creation and annihilation operators to qubit operators using, for example, the Jordan-Wigner transformation. And then when you're constructing your circuits, it's often useful to take advantage of the cancellation of z-strings to make your circuits and gates more easily implementable on the quantum computer. And that's it for this lecture. Thanks for tuning in.